The story of this paper is I spend a lot of time answering questions about simulations and the statistics associated with that. And in the last couple of years, we've talked quite a lot about the generation of passengers for simulation. Lutfi and I did some work on batches and Poisson arrival processes, and there's quite a lot of stuff, mathematics there, if you're interested in the background in it. So that's what the history has been. But basically what we're doing is we are creating a series of passengers in simulation. And we are using a random number generator to put those on a timeline. There are many different ways of doing it, but this is my simple example. So I've got a random number generator, and I put the people on the timeline, and those are the people that arrive at the lift lobbies and press the buttons and need to go to their destination. And the random number actually has an effect on the results. Yeah? And we have a range of random numbers, and it's a bit like modelling Monday or Tuesday or Wednesday, and you might have the same number of people in the building, but they all arrive slightly different times, and you get slightly different answers. And that's why we have this random number seed generator within our simulation, a lot of simulators. So actually that defines the random, the set of random numbers that are generated by the software. And if you run multiple simulations, you will get different results. Fairly similar, but they vary, and sometimes there are some outliers, which is highlighted here, and that's why we run multiple simulations. And we basically do multiple simulations, then we take the average of the average, yeah, which can get a little bit complicated. So in the real world, there is an element of chance. And if we're modelling the real world, we actually have to accept that, and we have to have an element of chance within our simulations. But what confuses people is that sometimes a better system will perform worse. Yeah? So you can end up, you can improve your door times by 0.2 of a second when your average waiting time goes up. Of course, if you improve your door times, you expect your average waiting time to go down, and that's really confusing for people. But in the long run, the better system will win. The explanation I try to give for this sort of counterintuitive results is to do with sample size. But if you think about the individual instant, if the door time is faster and the doors close quicker, there'll be sometimes occasions when someone arrives and misses the lift, whereas if the door lift had stayed over for a bit longer, they could have got into the lift. Yeah? So if you're just looking at individual instances, you do get these counterintuitive results. And the smaller the benefit, the more simulations you need to do to demonstrate that really there is a benefit. So if you improve the door times by a second, you can do 5 simulations and it will demonstrate that it really has an effect. If you improve the door times by 1/10 of a second, you might have to do 50 simulations to prove that there's a benefit. Yeah? There are various ways of approaching this. Quite a common one, I think the new ISO traffic analysis standard is going to be based on a nice simple constant profile. And what we've got here is a 2-hour simulation, constant demand, and the idea is that you remove the first 15 minutes and the last 5 minutes on the basis of that sort of the start and end effects, and then this bit in the middle in theory creates enough sample size for statistically valid results, though there isn't any mathematics behind to demonstrate that it is. And actually, even if you run a simulation this long and look at the average over that period, sometimes that gives you counterintuitive results as well. Yeah? So that's one way of approaching it. In Guide D, we like to have these transient profiles, which go up to a peak and then they come back down again. And then we're actually just looking at that peak 5 minutes, or the worst 5 minutes in that simulation, to look at what the waiting time is there. So it's actually a much smaller sample size, so we have to do multiple simulations if we're going to do that. The reason a little bit off topic, but the reason I like these transient profiles is it actually gives you an idea of what the queue lengths would be, because a lift system is not a steady state system. In reality, actually it goes up and down. So this is why I use those. But what I'm trying to do is understand how many simulations do we need to do to get statistically significant results. I happen to have the luxury of having a very bright young student come to work for me, so I set her this problem, and the following 8 minutes will be a lesson in statistics, and she'll teach you a little bit about her conclusions, which I'll talk about possibly implementing.
Thank you. Yeah, so the big question is, how many simulations do we need to complete? Because, as you know, it is very widely discussed and you have lots of different opinions on it. My first idea when tackling this was, why not simply look at the percentage difference between each moving average and wait until it's continually below a certain value? I mean, arguably that would be the best way of doing it, just thinking about it logically. You've got a set of results and you want to know by how much each of them are changing, and by how much, if you run more rather than less, how much that improves it. So as you can see in the last column, that's the difference in the percentage moving average. And it decreases, it does, but there's also variation in it. To do this, you would first calculate normal means, but you'd just do it in sequence. So you'd first calculate the moving average of the average waiting times. So you've got the first two results, and you calculate the mean to get the first average, in this case 6.1 plus 4.4, and then divided by 2 and you get 5.3. The next average you calculate also includes one more result because we're doing the moving average. So you've got 6.1 plus 4.4 plus 4.1, and then you divide it by 3. So that leads to your next result, which is 4.9. And this carries on, and so you do it for 4 and then 5 and then 6. The moving average is really important as it makes trends stand out. As you can see here, if only each average waiting time was plotted, it would be great variation and it would go up and down and there'd be no kind of consistency because it's just a certain value that you get. It doesn't really have any meaning if you look at it individually. So there'd be no way to understand the trend of the data as it's going along. This graph clearly shows us how quickly we can reach a consistent average of the data. So you've got 100 simulations and you can see it's still varying quite a bit, but as you go along, you've got 1,000 iterations and it's all evened out. The next way to analyze this data is to look at by how much each successive moving average is changing. If the moving average is roughly stable, you know that this average is likely to be a good representation of what all the data is like, because it's converging. So you know that that is going to be actually a good estimation of what your true value is. From the previous graph, you can actually see visually when the moving average is roughly stable. So as I was saying, about 1,000 simulations, that's roughly evened out. But calculating a value of percentage difference actually quantifies this for you. So if you didn't want to plot a graph, then you could have a numerical value that actually proves this for you instead. However, as you can see in this table, the moving average, it's subject to large variation. So it leaves an arbitrary decision as to how many repeated consistent values of the moving average are required before you're actually confident as a user in stating that they have the convergence that you require. Or, for example, what percentage difference is acceptable. In this instance, you can argue that convergence is achieved after 8 simulations. It's dropped down to 0.1%. And the moving average is consistently quite low. But if you do one more simulation and then take that into account, it jumps right back up, so it's 4.3 again. So you've just quantified it, and you've gone, okay, so I've stopped at 8, I'm happy with that, I've got 0.1% difference. Then you run one more, and all of a sudden you've got 4.3, so do you really know that it's actually finished? So these are the points at which the user may think that the data's leveled off from a graphical point of view, when in fact it hasn't. So that's the point. Each of those is where you'd get the 4.3% or any other number of increase, and that's not what you expect. So it's just where it trends back up when you're expecting it to be moving down again. And as you can see right at the very end, it looks like it's leveled off, but it does seem that it could be climbing back up again, but you've got no way to prove this unless you run another however many simulations. Another weakness of this technique, I feel, is that there can be no guarantee of how representative the calculated mean actually is of the population. So in this graph, after 15 iterations, the mean's 5.6. So that's where that's highlighted. And if you stop the simulations here, you would have no way of knowing that from 500 to 1,000 simulations, the average is actually 5. It's not 5.6, it's gone down. And that's just because you've run another 500. So which one's the true value? From a visual inspection, we're likely to trust that the 5 is actually the average. That is actually what we believe. And it makes sense because you've got 500 iterations to prove this. And all of that data backs up your new mean. Whereas you only had 15 values for the first one proving that one. You've got 500 backing you up now. But how do you know that the mean isn't going to trend upwards again? I mean, if you run 1,000, so off the end of this graph, if you run 1,000 to 2,000 simulations, how do you know it's not going to go back up again? So having no estimate of how likely the parameter is to be close to the population parameter, it's a disadvantage because it's unknown how much confidence you can hold in this result. And also, do you actually want to run an extra 500 simulations just to check, in fact, that the data's converged? It's not really something that you want to do. And then when does the user stop? Because there's no endpoint for that. So instead, I decided to look towards confidence intervals. I feel there are two very important definitions required in understanding confidence intervals. The first is population, which Lutfi talked about earlier. And the population is the total set of observations that can be made, so measuring the height of all the people on the planet. And then the second definition I really want is sample, because it's instead of taking everyone, I'm just going to take everyone in this room and measure their heights. In simulation particularly, it's not realistic to collect all of the data of the population. It would take far too many simulations and it would be too time consuming to actually be feasible. So this is when you'd use a sample. Parameters, for example, the mean and the standard deviation, are calculated whenever multiple simulations are run in order to give an overview of what the collected data is representing. So if you calculate a sample mean and then calculate the population mean, it's really probable that they're not going to equal each other, just as individual sample means won't equal each other either, because you've got different observations making up each of the samples. So if we believe that the population mean is the true mean, and you cannot calculate it, then you need an approximation. But how do you know how much confidence you can hold in this value? The sample mean will not necessarily be representative of the true mean. It may be including anomalous results, which is what Richard mentioned earlier, so it might be skewing the data. And the same is true for every other parameter, so you've got the variation and the standard deviation, not just the mean that this would be affected by. The reasons that these are different, there are quite a number, but it makes logical sense. I mean, the observations of the whole population will always remain the same, whereas different samples can be obtained depending on which observations make up each particular sample, but also the number of these observations made. So if you've got a sample of 8, the mean's going to be very different if you take 16, and then you've got that mean instead. So confidence intervals help us here. A confidence interval gives you two important pieces of information. It gives you a bound and a width of that bound extending either side of the sample parameter, for example, your sample mean. And it gives you the probability that the true parameter, so your true mean of the whole population, is actually located within that bound. So it gives you how close you are to the true value and the confidence that you can hold in that determination. So I'm going to look at confidence intervals using the mean average as our parameter. Each sample has a mean, so for samples of the same size, it's possible to plot the distribution of the values of these sample means. The confidence interval analysis is based on the assumption that the distribution of these sample means is normal. So the normal distribution, which looks like this, and it's commonly used in statistics. You'll find it pretty much underlying every theory in statistics. It's very, very important, and it occurs a lot in nature. So a confidence interval, this is the formula for it, and it's calculated based on n, the sample size, s, the standard deviation, and Z. Z is a Z value, and it corresponds to the confidence level. So when I was saying how much confidence you can hold in that result, these are a set of values, and you can have it for pretty much any confidence you require. So you've got 70%, which you wouldn't have much confidence in it, and then 99%, and they have a corresponding value, and that changes the width of your bound. A confidence level, so 70%, 80%, 90%, is the probability that the confidence interval contains the true value of the parameter. So as your confidence level increases, the confidence interval width also increases. And that's the consequence of having a more precise determination. So it's going to get bigger the more confident you want to be, because it can't say, oh yes, you've got 99% confidence in this result, but it's going to be more precise because it just doesn't make sense. The confidence interval calculation then gives bounds either side of the sample mean. So you've got the plus or minus. This is the bound width. So you've got X bar, that is your sample mean, and then plus or minus either side. So it's going to be an equal bound either side of your sample mean. So it states, for example, that there is a 70%, 80%, 90% chance of the population mean being within plus or minus a certain value of the sample mean. So as I mentioned earlier, the premise is based on the distribution of our average waiting times, or our sample means, being normal. The normal distribution looks like this on the left, and in reality, we didn't find that this was the case for our results. We found it looks closer to log normal distributions, which is slightly skewed towards the left. Another technique was examined to calculate confidence intervals based on log normal distribution instead of normal distribution, which isn't very common because nobody uses it. However, we found that the bounds produced were far too large and sometimes didn't even include the true value and ignored the sample mean. So you'd get something that was a bound, but it wouldn't actually include the sample mean average. It's expected that the data isn't of normal distribution. It's not always going to be perfect, things happen. But the main reason for this is that each average waiting time is always greater than 0. So you can't have the graph extending infinitely towards the left, because you can never have a minus number of average waiting times. So that leads to a skew where the right leg is much shorter than the left. The effect in our case was much less pronounced than the previous example on the screen. It actually looks more like that, which you can see is quite close to normal. We did run tests on it and proved that it is actually close enough to make an approximation that the data is distributed normally. So a calculation of the two-sided confidence intervals, so equal width on either side, is this. So it's X bar plus or minus Z multiplied by the standard deviation over the square root of the number of samples. And Z is obviously based on your certain confidence level, 90%, 80%, or whatever you choose. So for each extra subsequent simulation, it increases the sample size by 1 because you're adding 1 more to your sample. So you have one of a certain size, you start with 1, and then you take all the measurements from it, then you add another, and you calculate the moving average, as I showed you earlier. And so this then becomes the new sample mean, which you just follow based on your moving average. And then you calculate the standard deviation again. Because as the number of samples increases, generally speaking, your confidence interval will decrease, because then you're getting more precise results and you can narrow it down. You can see how you're improving with subsequent simulations. So the graph earlier, which showed the moving average, that's essentially the same theory behind this. The more simulations you do, the more confident you're going to be in your end result. So this means that your population parameters are actually located within a smaller margin for the more simulations that you run. And this can be utilized. So rather than arbitrarily choosing when the results are converging based on the population parameter, one decision on the width of the interval that you would be comfortable with and confident in is required. So this means each simulation run can use previous simulation results to calculate the moving sample parameters, and each subsequent confidence interval narrows down the exact position of your true result with your sample. In this setup, each simulation produced an average waiting time, a moving average calculated based on that and the previous average waiting times, and then the confidence interval bounds. So this is just the plus or minus, this is not the actual upper and lower bounds. So this is either side of the moving average waiting time that those results would be applied. So this would be implemented as a user would specify the confidence level. In this example, we used 95% and a margin of error. We chose 0.5 seconds for this. And these inputs would be placed in the program. So that's what in a result and a program you would put in and you'd choose, and then you'd get your results based on. As each successive iteration takes place, the sample of average waiting times increases. So each time the sample accumulates another average waiting time, the confidence interval's calculated for the chosen confidence level and then applied. If the margin of error is less than the mean average waiting time, then the program will terminate if the margin of error is less than the confidence interval bound specified by the user, then the program will terminate. But if it's greater, the program accumulates another average waiting time from a successive iteration and repeats the process up until the point where the margin of error is less than that specified by the user. So that's basically just applying it and showing what your upper and lower bounds would be. And implementation is what I just talked about earlier.
Okay.
Thank you.
So that was the science bit. For those who didn't follow the mathematics, what's it mean? So the acceptable range, the inputs to a software program become the acceptable range and the confidence level. So for example, it could be you're interested in the waiting time or any other parameter plus or minus 2 seconds with a confidence level of 90%, for example. Actually, what those values are is something that we probably need to discuss and debate. What are you satisfied with? Do you want to know your result plus or minus 1 second, or is that plus or minus a tenth of a second? If you're going to do a tenth of a second, then you're going to be simulating a lot of runs, and what confidence you need to do. And this is the implementation as Mia discussed. You're on a single simulation and you update your average waiting time and you just go around in a loop until you've got enough confidence. And you finish. And the technique we actually started off doing this with Monte Carlo simulation, and it's been very effective in using Monte Carlo simulation, and we're going to obviously implement it in dispatcher-based simulation. The benefit is you no longer need to say, I want 10 simulations, 20, you don't need to guess that number, you just say, I want my result plus or minus with this level of confidence. That's it.
Thank you, Richard.